Hello everyone. In this video, we are going to talk about plotting or creating a point cloud or convex hull of the reachable workspace for a robotic arm in CoppeliaSim. So here we have this KUKA robot, and this has 7 degrees of freedom. It's this guy here. You can see it has 7 joints, and here we have this minimal code that I modified from the original code it had. I made it absolute small as possible. And this one goes and randomly picks 50,000 points in the joint space of the robot from all of the 7 joints, which is kind of about 5.5, 5.6 sample points per range of each joint. And then creates the point cloud that is the XYZ points of the end effector, the points that the end effector can reach. It's not the dexterous, it's the reachable workspace. And this is really useful for many applications. I know my students in their capstone projects, they need to, for the robots they are designing, they need to show the workspace, and I want to show them how to do it here. So this is the robot, and you can replace it with your own robot. So let's talk about the script, and I am going to share this script under video description. So what do we do here? We need to bring the sim as always. We also, since we want to create a convex hull, we want to bring in the sim convex. My initialization, all it does, it calls this do calculation function, and this is the one that is doing everything. And by the way, before I even move on, let me show you the result. So let's go ahead and run. There we go. So this is the 3D point cloud. Now the point cloud are those white points that you see. And the convex hull is all of these tessellated surface. If you want, you can just plot the point cloud, okay? And get rid of this convex hull. So what does the code do? Let's go look at that do calculation. So here you create a bunch of variables. First one is check collision. Here, when we create all of these 50,000 points per each one of them, we check whether the robot, the tree of the robot, is colliding with anything in the scene, including the robot itself. So no self collision, basically, okay? And I'll show you how we do that. We basically do it with this guy called, let me show you sim handle all, this one here. So first we started as true, and then anytime if there is no collision, we check it at false, and then we add the points as one of the appropriate points to the point cloud. Use point cloud, yes. Extract convex hull, yes. You can make it false. This is the number of points. You can make it bigger or smaller. And then here are the handles of the joints. This we started as empty, and then we add all of the 7 joints here. The joints can have a low range, upper range, lower limit, upper limit, or a range. Or if they are cyclic, which we're going to see, then they don't have any limits, right? Especially here when all of them are revolute joints. Basically, a revolute joint goes negative 360 to positive 360. There is no limit. So we are not going to have any limit for it. We just go negative 2 pi to 2 pi. So here, look, this is what we do. And we also get all of the initial joint positions. And again, we start them all empty. Now we go from 1 to 7, and we go over each one of the joints. So we go to the get object and joint, and the index is increasing. So the assumption here is that in the tree of the robot, each joint has an increasing number from 1 to 7. So all of the joints are numbered, and they're increasing from 1 to 7. And you can see that here that these joints are attached to these links, and their numbers are increasing. If it's not exactly arranged like this, this part might give you an error. So what do we do now? Once we get the joint handle, let's say number 1, 2, and so on, then we go to that and look at the joint interval. It gives us a logical variable cyclic, which is true or false, and an interval. If it's cyclic, then we put here, look, the low range for that as pi and negative pi, and the high range as 2 pi. else we look at interval number 1, and then the second one is 2 minus 1. So this interval has two numbers in it, okay? So we get that. We also get the joint position right now before anything starts, and we store them as joint initial positions. Then we need to get the tip and the base of the robot, okay, because we need them later. We'll see when we need to do the point cloud, we need the base and elsewhere. So I'll show you where we need the tip and the base. So this is the end effector, this is the base of the robot. Then what? Now here we have this variable called robot collection that basically is all of the robot. This is the tree of the robot. This is the whole robot, okay? And we need this for collection, for collision detection and checking. So we create a collection and we pass the whole robot collection to it. And first we create it, and then we add to it basically sim handle tree. We add the whole tree of the robot to this collection. And what is this base? This base is basically tells you this is the tree of which robot. Right now, the only robot I have is this KUKA, and there is only one link that is the base. So right now, and the base is basically is defined already here. But if you have several robots, each one of them has its own base and its own tip. So here you have to see which one of them you are going to has as the reference. This is the tree of which object. So this is the object. This is the base of the whole tree. These points here, these are the points that we will have for the point cloud, okay? So this point here, I added a comment for it down, and that is, let me show you here. So I said point is the numerical storage of all reachable points. So this can basically be added here as well, right? So this is the vector that stores all of the points, x, y, z of them, and then next x, y, z, next x, y, z, and so on when we use them for the point cloud or the convex hull. This other one called point container, this is used if you do not use the generated point cloud. If instead you want to create your own kind of point cloud and you draw a bunch of spheres in place of all of these points, and here you can give it specific visual properties, like what? You can give them a type, which again here is a sphere. Points, size, you can say how big those points are. You can give them a duplicate distance. What is duplicate distance? This is basically the distance that if you move away from one point and any other point is inside this distance, it is considered a duplicate and those points will be merged. And then relative to what? Of course, relative to base. How many points do you really want maximum to plot for this is this number. I can change it. And then what color? Here I want all of those spheres that are replacing the point cloud to all be white. If you want, you can make them all black. And I'll show you how this one works. So let me change this to black and I'll show you exactly how it is working. The only thing, maybe I want to change the size, but I can come back and change it. So right now, we do have the true value for this use point cloud. Therefore, this portion will not work. You just get a bunch of white dots as I showed you in the point cloud. Look here. So you just get the white points. And to make the white points more clear, let me for a second get rid of the convex hull so you can see that there are only a bunch of white points, which is my point cloud. Let me run it for you. There we go, you see? So this is the point cloud without the convex hull. And if you want, you can get rid of this and replace those points by a bunch of different shapes other than points, by spheres, anything with different colors, different sizes. So let me show you that one here. If I go ahead and make this one also false, now ideally those black circles should replace. So let's go ahead and run that. Now it's not going to be as beautiful as the point cloud. There we go. Look, you see that? So you get a ton of black circles here, right? So these options can help you visualize the point cloud any way that you like. And in this case, I would rather not deal with all of those circles. The point cloud is good itself. And I guess the convex hull is really good for seeing surfaces rather than points. And I'm going to check that. So, okay, now that we've seen all of this, this is the major part. This is the major loop. So it goes from 1 to 50,000 or whatever you want. And it creates a variable for the joint value from P1 to P7, each one for one joint. So look, you go to joint limit number 1, right? This is the low limit of joint 1. You multiply the range of joint 1 by a random number, which is between 0 to 1, add it to the low, so you get somewhere between lower and upper limit of joint 1. Yes? And once you create that P1, what would you do next? Next, you go and say, hey, go and for joint number 1, set it to value P1. You see that? And by the way, what is this semicolon? This is an interesting one because we have not used a semicolon in the past. So unlike like MATLAB or C, it is not really ending or suppressing anything. When you put this, it allows you to add another line of code in the same line, basically. So here I added this comment for you that it doesn't end the statement. You can just place multiple statements on the same line, right? So we generate a random number between the low and the lower and upper limit of joint 1. We set joint 1 to that value and then do it for all the other joints. So now the robot is exactly in that random position. And now, first we start colliding as false, but then what we do is first we get the object matrix of the tip. This is the 3x4 position and orientation of the tip. So the first 3x3 submatrix is the orientation of the end effector or tip, and the last column, which are numbers 4, 8, and 12 of this matrix, are X, Y, Z of the tips, right? So you get the tip position, and once you get the tip position, what would you do? Now, look what you do here. You say if check collision, which is what we want to do here. We said, yes, you should check collision, okay? Because we want to get the self-collision or collision with any other object in the scene. We want to get it out of the workspace. So it says what? If you want to check collision, what would you do? Look at the robot collection and sim handle all. What does that mean? It means check everything, even the robot tree itself. If it is not equal to 0, then so this command returns a 0 if no collision exists. It returns a non-zero if a collision exists. So if it's non-zero, means there is a collision, then put the colliding to true. Yes? So initially you started at false, but then you run this for it, and it goes to true. And why would you do that? So when you go back to the next point, next random point, remember you have to do this 50,000 times. You started at false, then if something happens, if the collision exists, you change it to true. Now, if not colliding, which means if there is no collision, then go ahead and add X, Y, and Z of that point to the points, okay? So this is what? This is X of the tip, correct? And then similarly, you have Y of the tip and Z of the tip, okay? So add them together, and as I said, the structure of this point here, let me show you. This point, the structure of it is like this: X1 and Y1 and Z1, and then X2 and Y2 and Z2 and dot, dot, dot. Okay, so that is the structure of what? That is the structure of the point here. So you store that point as something that has no collision, and we can use it for plotting. And then if I don't want to use the point cloud, I'm going to add that point also to the point container. And point container, remember, it was the collection of all of those black points. So we only store them if we don't want to use the white point cloud. Fine. So we got all of the points. Now we got all of the points. What do? Before we plot the point cloud and before we do the convex hull, first we reset all of the joints to their initial position. So you see why initially we stored the initial positions here. Because however we started, when we want to draw the point cloud, we want to go back to that configuration, then draw the point cloud around it. We don't want to end up with robot in a different pose and then draw the point cloud. We store whatever we have. We do all of our movements and all of the generation of point cloud. We go back to it. Then we draw the point cloud around the initial configuration or pose. Okay, so here is just to restore it. Now we create the point cloud. If requested, how? We use the command create point cloud. And what you need to pass to it is the point size, the maximum number of points per circle, if there is any option, and the parent handle. So here I create a point cloud, and then I'm going to pass all of those stored points to the point cloud. There we go. So I create the point cloud. First it becomes empty. Once I insert the points into it, now it is going to plot all of those beautiful white points. And then if there is a convex hull, then use the sim convex hull.q hull. Pass all of the points to it. It gives you back the vertices and the indices of all of the surfaces generated between these points. And look here, once you get the indices and vertices of the tessellation, right? Then you want to say how you want to connect these together. Here we use the command create shape and say 3 0 vertices and indices. What does this 3 mean? 3 is the type of the shape. 3 means 3 edges, which means a triangular face. So create triangular face from these vertices and indices. And of course, no option here. So it is going to create a bunch of triangles for the convex hull. And then here we change basically the properties, visualizations of that shape. Like what? The first command is called align shape BB or bounding box. This one aligns the shape, which is in this case the convex hull. It is going to align it with the specific bounding box. So what are all these numbers? These numbers are the X, Y, Z, alpha, beta, gamma, and a flag of the bounding box that you want to align your shape with. And you see these are all 0 numbers, so it is really the word frame here. Then because it creates a shape, you don't know how to exactly position it and orient it, but this one will tell you how to position and orient it. Then here you can change the color of the bounding box. You see here I picked 010, which means green. And then you can change the opacity of it. And here I use the opacity of 0.4. If you make this 0, then you are not going to see through the convex hull. Right now, if I run it, you see the convex hull is semi-transparent. I can see all of those white points through it. But if I make it 0, I cannot see through it. If I make it close to 1, it is almost like nothing, like glass. Okay, so this is how, with this minimal code, you can create the shape of your workspace, whether point cloud, whether convex hull, or both. And you see clearly your convex hull is made of a bunch of green triangles that are semi-opaque. So, as I said, I will share this script under video description for you. Take a look at it, learn from it. You can replace this robot with your own robot. You can even add obstacles in the environment, right? So I can go to the furniture here. I can go to the chair. I can grab a chair, or I can grab a sofa, right? Put it right next to this one. And then what? Then it is also going to check the collision with this one. So now not all of the workspace original one is going to be useful. Look here. You see? Look. Now, if you see, the shape is changed a little bit, and this portion of it that went inside is removed from the rest of the workspace. Thank you so much. I'll see you in the next video.